Are you seeing the full screen or presentation mode?
Yeah, we've got
full screen. Full screen.
Yeah,
thank you very much. Okay.
Fine.
Okay, so today I'm going to talk about the MCCIP report on oxygen. This is the second time we have produced this report. The first was in 2020. I just want to acknowledge the co-authors here. It was very much a team effort. And the updates we've made on this MCCIP report in 2023 is we've provided some new data supplied by Tom Hull and some new model outputs supplied by Sarah Wakeling. Whoops. So the first thing I want to do is just get everyone on the same page about what controls dissolved oxygen in marine waters. So it's controlled by a combination of both physical processes, outlined here on the left-hand side, and also biological processes shown here in the figure on the right-hand side. So starting with the physical processes, we have air-sea gas exchange, which transports oxygen between the atmosphere and the ocean. Once in the ocean, temperature strongly controls the solubility of dissolved oxygen like any gas. So with oxygen being more soluble in colder waters and less soluble in warmer waters. So it's the boiling kettle effect, if you like. For example, if we heated seawater up by about 1 degree C, we would actually cause dissolved oxygen to decline by about 5 micromoles per kilogram. In the ocean, we have vertical mixing, which exchanges water between the surface mixed layer and the bottom mixed layer, and this also redistributes oxygen vertically. And also in bottom waters, we have horizontal transport, which advects water of different properties across the seabed. For biological processes, we have processes that both produce and consume oxygen. So photosynthesis produces oxygen, and we have a range of processes that consume oxygen, including respiration by organisms and respiration by bacteria, which remineralizes organic material back into its inorganic constituents. So in the sunlit layer of the surface ocean, typically photosynthesis is greater than respiration. We have net production of oxygen, which means our surface waters are typically very well oxygenated, also due to air-sea gas exchange. However, when we get into the kind of the darker layers of the ocean, typically respiration is greater than photosynthesis, and therefore we have net oxygen consumption. And this is where we tend to see lower oxygen concentrations relative to the surface waters. The organic material that's here that's degraded is actually originates from the surface ocean. And so this material reaches into the deeper ocean, and this is where it's degraded back into its inorganic constituents, consuming oxygen. Some of that material gets to the sediment, and if that sediment is resuspended through processes such as storms or through fishing gear, for example, that can promote oxygen consumption. And some of that material may get into the seabed, and that also results in oxygen consumption within the sediments. I just want to emphasize at this point that it really is a combination of both the physical and biological processes that control dissolved oxygen in the marine environment. And that's to really understand oxygen dynamics, we have to understand these processes individually, but also the interaction between these processes. So why do we care about oxygen? So when considering the health of an ecosystem, we report oxygen in milligrams per litre. And so we consider that a well oxygenated, healthy ecosystem has oxygen at around 8 to 10 milligrams per litre. However, once oxygen starts to decrease, we get to some very well defined thresholds. So for example, we can define oxygen deficiency when oxygen is less than 6 milligrams per litre, hypoxia when oxygen is less than 2 milligrams per litre, and anoxia when oxygen is less than 0.5 milligrams per litre. We all know that marine life requires oxygen, and thus a decline in oxygen can have a really adverse effect both on the metabolism and the physiology of these organisms. The figure on the right-hand side indicates the oxygen threshold considered to be sublethal for different groups of organisms, and this means that below these thresholds of oxygen, organisms are likely to experience reduced growth, reproduction, physiological stress, forced migration, and potentially changes to their life cycles. So we really care about oxygen to think about the kind of ecosystem health. So in coastal and shelf sea waters, water column structure places a really strong control on oxygen dynamics. So in a permanently stratified water column shown here on the left-hand side, or with the red lines on the right-hand side, the properties in the surface and the bottom waters are the same. These waters are well ventilated and typically well oxygenated. However, if we think of a seasonally stratified water column, which is a significant part of our UK waters, we have a thermocline which separates the surface layer from the bottom layer. And that also then stunts or slows down mixing between this well-oxygenated layer and this bottom layer. And remember, this bottom layer is where we have net oxygen consumption, and this is the layer that we're concerned about in terms of thinking about oxygen dynamics in shelf seawaters. So what is already happening? These are some observations from a smart buoy in the North Dogger Bank in the North Sea, and they reveal a seasonal trend in surface oxygen in green and bottom oxygen in black. And we can see that for the most part, dissolved oxygen declines in the bottom waters relative to surface waters during periods of stratification, again, because that water is isolated and there's restricted exchange with the atmosphere. In this data set in 2007, dissolved oxygen concentration in bottom waters declined to near oxygen deficient levels towards the end of the summer due to that net oxygen consumption as well as the isolation from exchange with the overlying atmosphere. If we move over to the Celtic Sea, this is some observations from the Celtic Deep Smart Buoy and the Celtic Deep Benthic Lander, again showing oxygen concentrations in surface waters in red and in bottom waters in blue. And again, we see that there is departures in oxygen content in these two layers during the summer stratified period. In this case, in 2014 and 2015, dissolved oxygen declined below oxygen deficient levels as shown here in the blue. And this was near the end of the summer stratified period in the Celtic Sea. So to our knowledge, this was the first report of oxygen deficiency in the Celtic Sea. However, we do have low confidence in both the spatial extent and also frequency of oxygen deficiency in UK marine waters, simply due to the fact that there's a lack of sustained observations, especially outside regions of the North Sea. So due to this lack of observations, we certainly rely heavily on either model reanalysis or numerical simulations to predict or to project the future of oxygen deficiency or hypoxia in UK marine waters. This figure shown here is some model reanalysis published in 2016, and it suggests that there's large areas of the Northwest European shelf that are vulnerable to oxygen deficiency, specifically regions in the Celtic Sea, the Irish Sea, the English Channel, and also coastal regions around Scotland, and that's with 100% deficiency as defined here in the regions in red. So what could happen in the future? So for UK shelf waters, numerical models, in this case NEMO-IRSEM, specifically designed to represent processes in coastal and shelf sea waters, project a decline in oxygen concentrations in all UK marine waters by 2100, where the black lines in these figures are the annual mean concentration and the grey lines are the minimum monthly concentration of oxygen within the bottom mixed layer, again within this layer that's below the thermocline. So under RCP at 0.5 and by 2100, oxygen is predicted to decline by up to 9% in the English Channel, the Southern North Sea and the Irish Sea, depicted by the red arrows here. It's predicted to decline by up to 6% in the Central and Northern North Sea regions and in the Celtic Sea, shown here in the orange arrows. And oxygen is predicted to decline by up to 3% in the Irish shelf waters and the Irish shelf waters and the Shetland shelf waters, again shown here by the green arrows. Note that the dashed lines represent the threshold of oxygen deficiency, and you can see that oxygen deficiency is reached by 2100 in 6 out of the 8 regions reported here. Just to note, the lower decline in oxygen projected in the Irish shelf and the Shetland shelf are due to the exchange of water between the shelf waters and the adjacent open ocean regions. So that exchange is important in terms of ventilating these shelf sea waters. So what are the drivers of the projected decline in oxygen? Well, we have high confidence that ocean warming will decrease the solubility of oxygen in marine waters. And indeed, numerical models indicate that up to 75% of the projected decline in oxygen is due to the reduced oxygen solubility, with the rest being due to other processes. We have medium confidence that stratification will lead to a decline in oxygen in the future. And you may ask why it's only medium confidence, and this is regarding the uncertainty of the role that increased stratification will have on reducing the amount of nutrients available to phytoplankton, therefore potentially reducing photosynthesis, and therefore reducing the amount of organic matter available that fuels oxygen consumption. We have low confidence in the contribution of these other processes leading to a change in oxygen. So, for example, the response of biological processes to warming in terms of their speed at which they are processing or metabolizing, and also the frequency and intensity of storms, which may actually mix and ventilate bottom waters. So we have low confidence in the impact of these different processes on the direction and magnitude of change of oxygen. Finally, challenges and emerging issues, and we have 3 challenges when considering oxygen. So assessing the occurrence, the frequency, and also the spatial extent of oxygen deficiency in UK waters is hampered by the lack of long-term data, especially in regions outside of the North Sea. We do not fully yet understand all of the processes contributing to the decline in oxygen in the marine environment, and that's also especially related to the interaction between these processes. And we don't fully understand the impact of the anthropogenic activity relative to natural variability on oxygen. Both the lack of observations and also the lack of this mechanistic understanding really creates an enormous challenge for ocean models that are tasked with making projections of how future ocean dynamics will actually work. In terms of opportunities, we do have an opportunity with the recent advances in the use of autonomous underwater vehicles, or AUVs, are commonly known as gliders. That can dramatically increase the amount of data that is available in UK marine waters. And there have been rapid technical advancements, has really improved, first of all, the longevity of these instruments, as well as the sensor capability. And certainly the scientific community is also increasing their skill and also in handling these data sets, but also interpreting these data sets as well. And this has been recently demonstrated through the Shelf Sea Biogeochemistry project and also the Alter Eco project. Thanks very much, and I look forward to questions.